Last time in our 2-tower recommender, we still leaned on the same crutch every model in this course has used. We had the answer key, labels, this user clicked, that one didn't. But here's a question that breaks the whole setup. What do you do when there is no answer key? Nobody can hand you the correct move for every frozen instant of a video game, or for a robot deciding how to take its next step. Today, we walk back into the train stop on our pipeline, but we throw out the labels. The only thing our agent ever gets to see is a reward. This is reinforcement learning, and we're going to teach a little cart to balance a pole using nothing but trial, error, and a method called reinforce. Think back over everything we've built: image classifiers, sentiment models, recommenders. Every single one learned from labeled answers. We showed it the input, we showed it the truth, it minimized the gap. Reinforcement learning has none of that. There is no truth to point at. There's just a world, an agent acting in it, and a score. So the train stop gets reimagined. Instead of here's the input, here's the right output, the only signal is reward. The cart moves left or right, the pole tips a little, and the environment says, you survived one more step, +1. That's it. No gradient pointing at a correct label, just a number that goes up when things go well. And it's a loop. The agent looks at the state of the world, picks an action, and the environment responds with a new state and a reward. Then it does it again. State, action, reward, repeat thousands of times. Learning happens because the loop turns, not because someone graded each step. The brain of the agent is something we call a policy, and a policy is just a neural network, the same kind we've built all course. It takes the state, 4 numbers describing the cart and pole, and it outputs probabilities. How likely should I push left? How likely should I push right? State in, action, probabilities out. Now here's the strange part. There's no correct action to train toward. Pushing left isn't right or wrong in the moment. It only becomes good or bad depending on what happens next. The same move can save the pole in one episode and doom it in another. We can't supervise individual moves. We can only look at outcomes. Did this whole run pay off or didn't it? That's the core idea of reinforce. And it's beautifully simple. Play a whole episode. If it went well, if the total reward was high, nudge the network to make the actions it took more likely. If it went badly, push those actions down. Good runs reinforce their behavior. Bad runs get discouraged. Over many episodes, the lucky and good patterns float to the top. One refinement. When the pole finally falls, the actions right before the crash deserve more blame than the ones at the very start. So we use discounted returns. A reward now counts fully, but a reward far in the future is multiplied by gamma, a number just under 1, again and again. Rewards soon matter more than rewards later. Each action is judged by the discounted future that followed it. And the loss this creates isn't anything model.compile knows how to do for us. It's negative log probability times return, summed over the episode. So we reach for the tool from our scientific computing episode, gradient tape. We record the forward pass, build this reward weighted loss by hand, and let autodiff do the rest. Custom loop, custom loss, exactly what the tape was made for. Let's go read it. Here's the whole agent, about 60 lines across 3 pages. Top imports the environment and the policy network. Middle, the discount helper and 1 episode of acting. Bottom, the reinforced loss, the training loop that runs hundreds of episodes. And the plot, no model.fit anywhere. We drive every gradient step ourselves. Page 1. We make the cart pole environment with Gymnasium, the maintained successor to OpenAI Gym. And we build the policy, a tiny sequential model, 1 hidden dense layer of 24 RealU units, then a dense 2 with softmax, 2 outputs, 1 probability per action. We grab an Adam optimizer and set gamma to 0.99 for discounting. That's the entire setup. Page 2, discount rewards, the whole function on one page. We walk the list of rewards backwards, accumulating. Each step's return is its own reward plus gamma times the running total of everything after it. Then we standardize, subtract the mean, divide by the standard deviation, so the numbers are well scaled. This is the how good was the future after this action signal. Still page 2, run episode, the part that actually plays. We reset the environment, note the new gymnasium API returns the state, and an infodict, then loop, feed the state through the policy to get action probabilities, sample an action with tf.random.categorical, and store the log probability of the action we picked. Step the environment, bank the reward, and stop when the poll falls or we hit the time limit. We return the stored log probs and rewards. Page 3, the crucial detail first on we run that whole episode inside a gradient tape. Because run episode calls the policy network, the tape watches every operation that produced those log probs, so it can trace gradients back to the weights later. This is exactly why we don't use model.predict. We need the forward calls recorded. Then the loss. We turn the rewards into discounted standardized returns, and the reinforce objective is negative log prob times return, summed over the episode. Minimizing it pushes up the log probability of actions that led to high return and pushes down the rest. Then the two lines we've seen all course for custom loops. Tape.gradient to get the gradients, optimizer to apply gradients to take the step, and the outer loop. Run this for many episodes, track the total reward each time, print progress, and keep a rolling average. Cartpole v1 lets an episode run up to 500 steps, and we count it solved when the average reward over the last 100 episodes crosses 475. When that hits, we stop and plot. Watch the terminal. Early on, the agent is hopeless. Reward around 20, the poll falls almost instantly, but the curve climbs. By a couple hundred episodes, it's holding for hundreds of steps, and near episode 280, it's spinning the full 500 step cap, and we see solved. No labels touched it. It learned a behavior purely from reward, and that's the leap. We just made a network create behavior. Next time we push further, instead of behavior, we make models create whole new things. Images out of noise, generative AI, GANs, VAEs, and a first glimpse of diffusion. See you there.